atmosphere. Well, indeed, space-time is an entity, and one of its properties is that it can be distorted or bent by a gravitational field. We know that gravity bends or distorts space-time and light by virtue of the fact that we're able to see stars which we know should be blocked from our view by the sun. Referring to the graphic here, the solid line denotes the position of a star that's located behind the sun, and the dotted line shows its position as viewed from Earth. This is made possible because the sun's gravitational field distorts the space-time and light around the sun, allowing us to view stars which should be hidden from view. We know that gravity distorts time by virtue of the fact that if we take two identical atomic clocks and keep one at sea level and take the other one up to a high altitude, when we bring them both back together, they reflect different times. The difference in this passage of time is caused by the fact that a gravitational field weakens the further you get from the source. So the atomic clock which was taken to the high altitude was exposed to a less powerful gravitational field than the clock which we kept at sea level. The effect of a gravitational field on space-time is something that we've been able to observe, but not to experiment with. This is due to our inability to generate a gravitational field. And up until this point in time, great mass, such as a star, planet, or moon, was the only source of a discernible gravitational field that we're aware of. So just as the gravitational field around great mass, such as a planet, distorts space and time, any gravitational field, whether naturally occurring or generated, distorts space and time in a similar manner. Now, the great benefit of generating an intense gravitational field is not only can you turn it on, but you can turn it off. If we refer back to our original illustration of space-time distortion, we can see that when we generate an intense gravitational field, we can distort the space-time and in turn the distance between the point where we are and the point where we want to be. We can then position ourselves at the point where we want to be and then stop generating the gravitational field, allowing space-time to return to its natural form. In this manner, we can travel great distances with little linear movement, and this is how space-time distortion translates into reduced distance. Now back to our original question, how is it possible to cross the vast expanses of space required for interstellar travel without exceeding the speed of light? This is accomplished by generating an intense gravitational field, distorting space-time and allowing you to cross many light years of space in little or no time and without traveling in a linear mode near the speed of light. The next question is, how do you generate a gravitational field? Up until this point in time, I've used the term generate to describe the capability of producing a gravitational field, but since I'm not aware of any way of creating a gravitational field from nothing, a more accurate term might be to access and amplify a gravitational field. And this is what I mean when I use the term generate. To understand how gravity is generated or accessed and amplified, you must first know what gravity is. There are two main theories. The wave theory, which states that gravity is a wave, and the currently accepted theory of gravitons, which are alleged subatomic particles that perform as gravity, which is total nonsense. Well, gravity is a wave, and there are two specific different types of gravity, gravity A and gravity B. Gravity A works on a small or micro scale, while gravity B works on a large or macro scale. We are familiar with gravity B. It is the big gravity wave that holds the Earth as well as the rest of the planets in orbit around the Sun and holds the Moon as well as man-made satellites in orbit around the Earth. We are not familiar with gravity A. It is the small gravity wave which is the major contributory force that holds together the mass that makes up all protons and neutrons. Gravity A is what is currently being labeled as the strong nuclear force in mainstream physics, and gravity A is the wave that you need to access and amplify to enable you to cause space-time distortion for interstellar travel. To keep them straight, just remember that gravity A works on an atomic scale, and gravity B is the big gravity wave that works on a stellar or planetary level. However, don't mistake the size of these waves for their strength, because gravity A is a much stronger force than gravity B. You can momentarily break the gravity B field of the Earth simply by jumping in the air. So this is not an intense gravitational field. Locating gravity A is no problem because it is found in the nucleus of every atom of all matter here on Earth and all matter anywhere else in our universe. However, accessing gravity A with the naturally occurring elements found on Earth is a big problem. Actually, I'm not aware of any way of accessing the gravity A wave using any Earth elements. whether naturally occurring or synthesized, and here's why. We've already learned that gravity A is the major force that holds together the mass that makes up protons and neutrons. This means the gravity A wave we are trying to access is virtually inaccessible as it is located within matter, or at least within the matter that we have here on Earth. However, the Earth is not representative of all matter within our universe. The residual matter which remains after the creation of a solar system is totally dependent on the contributing factors which were present during the creation of the solar system. This is true whether you believe that the origin of the universe was an evolutionary event or that a supreme being caused this event to happen. The two main factors which determine what residual matter remains after the creation of a solar system are the amount of electromagnetic energy and the amount of mass present during the solar system's creation. Our solar system has one star, which is our sun, but the majority of solar systems in our Milky Way galaxy are binary and multiple star systems. In fact, many single star systems have stars that are so large that our sun would appear to be a dwarf by comparison. Keeping all this in mind, it should be obvious that a large single star system, binary star system, or multiple star system would have had more of the prerequisite mass and electromagnetic energy present during their creations. This makes it possible for these systems to possess elements which are not native to the Earth. Scientists have long theorized that there are potential combinations of protons and neutrons which should provide stable elements with atomic numbers higher than any which appear in our periodic chart, though none of these heavy elements occur naturally on Earth. 88 of the first 92 elements on the periodic chart occur naturally on Earth. Some heavier elements do occur in trace amounts, but for the most part we synthesize these heavier elements in laboratories. Generally speaking, the stability of these synthesized heavy elements decreases as their atomic number increases, but experiments at the Lab for Heavy Ion Research in Germany have shown that this may only be true up to a certain point, as the half-life for element 109 is longer than that of element 108.